In this video, I'm going to talk about infinite series. So this is a series is the sum of the terms of a sequence. So if it's infinite, we are adding up an infinite number of terms. So before I get into the math of this, I want to show you an example. So geometrically, let's say we have a square, and this square is 1 unit by 1 unit. Okay, and I'm going to start partitioning this square into parts. Okay, so let's say I partition it into 2 parts. So if this whole thing is 1, that's going to be 1/2. So if I wanted to find this area, we're just going to call this S1, and we'll talk about notation later, would be 1 times 1/2, or 1/2. Okay, we'll partition it again. So I'm cutting the other 1/2 and 1/2. So this area is going to be 1/4. So if I add this area and this area, I'm going to have 1/2 plus 1/4, which if you get a common denominator is going to be 3/4. Okay, we'll cut that extra 1/4 into halves, so that's 1/8. So we'll have 1/2 plus 1/4 plus 1/8, which is 7/8, and maybe you're seeing a pattern. Okay, and we'll add on one more half, so this is 1/2 plus 1/4 plus 1/8 plus 1/16, which is 15/16. So geometrically, if I keep going, we're going to get half and half and half and half and half and half, but it's still only going to occupy the area of this square. So even though we're adding an infinite number of terms, the sum of this is going to be 1. We can look at what we call the partial sums, which is when we add part of a series, to see that there's a pattern with these partial sums. If I wanted the formula for the nth partial sum for this series, the denominator is 2 to the n, the numerator is 1 less than that. Okay, if I look at the limit as this goes to infinity, the sum of this infinite series is a finite value of 1. So that's what we're going to be exploring over the next couple of weeks, is whether series have a sum or not. So we have a special name for whether a series has a sum or does not, and that's whether we consider the series to be convergent versus divergent. So for a series to be convergent, that is an infinite series that has a sum or a limit, and we just saw an example of a convergent series. Graphically, if you were to look at the partial sums, it would level off to some value. Now, sometimes we'll be able to find that value, sometimes not, but we're mostly interested in whether we can find a value or if it has a limit or sum. On the other side of it, if it does not have a sum or a limit, we consider that to be a divergent series. And graphically, that can look a couple of different ways. We could have a series with the partial sums that just keep increasing or keep decreasing. It's not going to hit a limit. We can have one that just keeps bouncing around. Okay, and if it's not approaching one value, we consider that to be divergent. So that's what we're going to be looking at over the next couple weeks, is whether a series is convergent or divergent. One way to investigate this, and we'll come up with much better tests, but this is a good illustration to begin with, is something called partial sums. So partial sums, and we saw this notation, Sn is the nth partial sum. So in my previous example, when I showed the sum of 2 terms, that was S2. If there is a limit for the partial sums, then the series is going to converge. If the partial sums doesn't have a limit, then the series diverges. So we're going to first look at the series from 1 to infinity of 1 over k times k plus 1. So we're going to generate the first 6 terms of the series. So remember, in sigma notation, we always start with this value. So I'm going to start by plugging in a 1. So I'll have 1 times 2 on the bottom. If I plug in 2, my k is 2, so that's 2 and 3, and so on. So we get these values. Next thing I'm going to do is simplify those. Okay, next I'm going to find the first 5 partial sums. To do this, I'm going to make a chart to organize. I'll have n here and Sn over here. Well, if n is 1, then Sn is the first one term, which is just 1/2. Okay, 2 is going to be 1/2 plus 1/4, which if I get a common denominator, 1/2 plus 1/6. If I get a common denominator, we'll get 3/6 over 1/6, which is 4/6, which we're going to go ahead and reduce to 2/3. The third partial sum, we're going to take that and just add on another term. The next term is 1/12. If I get a common denominator, we get, multiply this by 4 and get 9/12, which reduces to 3/4. So we'll go ahead and do the next 2. And the result is my S4 is 4/5, S5 is 5/6. So there's definitely a strong pattern here. So we can come up with a formula for Sn. So plugging in these values to get a result of these ones, well, you should notice that the numerator matches my n, and my denominator is 1 bigger than that. So my expression for Sn is n over n plus 1. Does it converge? Does it have a limit? Yes, sure does. So if it has a sum or a limit, then that means the infinite series converges. And it's going to converge to whatever the limit of the nth partial sum is. Okay, well, algebraically, those have the same degree, so this is 1. Numerically, looking at my chart, those values are approaching 1, so that is our sum. So our next one is the series -1 to the n plus 1. So my first 6 terms, if I plug in a 1, my exponent is a 2, so it's going to be a positive 1. If I plug in a 2, that becomes 3, so I'm adding a -1, then a positive 1, -1, and so on. So these partial sums are pretty easy to generate. Okay, if I add the first 1, we get 1. If I add 1 and -1, we get 0, 1, 0, and 1. Okay, so there's not really a great formula. You can get creative with it. I'm just going to say if n is even, my Sn is 0. And if n is odd, Sn is 1. So since this thing is bouncing around, it's not going real big or real small, but it's bouncing around, which means it does not converge. So the partial sums don't converge, so the series does not converge. Okay, so we'll get one more infinite series and investigate the partial sums. If I start with 1, we get 2 to the 0, which is 1, so we have 1/4. If I plug in 2, we get 2/4. If I plug in 3, we get 4/4 and 8/4. Okay, so these sums if I add 1, we get 1/4. If I add 2, we get 3/4. If I add 3, we get 7/4. If we add 4, we get 15/4. So unlike some of the previous examples we've seen, these numbers just keep getting bigger and bigger. So if I look at the limit of those sums, the limit's infinity. It keeps getting bigger and bigger and bigger, which means this series diverges. So that's investigating the partial sums. We'll look at many other tests throughout the next couple weeks.